Hello and welcome to our lesson on library of functions and piecewise defined functions. This is going to be from section 2.4 in our Precalculus text. Let's get started. First of all, notice that I've titled this parent functions. When you're covering transformations of functions, these are referred to as parent functions, but it is like a library of functions that you're going to run into. So we'll start with the name and then an example of what the function would look like. The first example of the graph here is a constant function where f of x would equal to some constant b. Notice that that is going to produce a horizontal line. The next graph is an example of the identity function. This function is represented by f of x equals x. Now the reason it's called the identity function is because whatever number you plug in for x, you're going to get that same value back for y. This is also a linear function. Next we have our absolute value graph. This would be an absolute value function where f of x would equal the absolute value of x. It is important to note that v is for value. An absolute value function will always make a v. Our next graph is a square function because f of x equals x squared produces a parabola. So again, this is a square function. It will always make a parabola. Four more to go. Next we have our square root function in which we have f of x equals the square root of x. Next we have a cube function where we have f of x equals x to the third power. Next we have our cube root function. Notice that the cube root function looks like a cube, but it squiggles from side to side. And the function notation would be f of x equals cube root of x. And last but not least, we have the reciprocal function where we will have f of x equals 1 over x. Now that we've covered the library of functions, we need to talk about piecewise functions. Now, a piecewise function is going to, of course, have function notation, but the reason they call it a piecewise is because there's more than one piece, and you have to be pretty wise to know which piece to use. So here we have an example, f of x equals x squared, where x is less than 0, or f of x is 2x minus 1 when x is greater than or equal to 0. In your piecewise function, at the right-hand side, you're going to have a set of inequalities. Those inequalities will determine which piece to plug x into. I like to call it the test zone because you have to test each x to tell where to put it. And the inequalities should restrict each x to plug into only one piece of the function. So for our first example, we want to evaluate f of negative 2. So we're going to go to the test zone and test this x to see where to put it. So for the first inequality, we would say, is negative 2 less than 0? If that's true, that's what you do. And I believe negative 2 is less than 0. So we're going to plug into the top piece and replace x with negative 2, and then we work it out. And that's evaluating a piecewise function. Let's do another. If we want to find f of 0, again we need to take this x value to the test zone and test it to see where to put it. So, is 0 less than 0? That is a false statement. Is 0 greater than or equal to 0? That is a true statement. And I said wherever it's true, that's what you do. So in this case, we're going to replace x with 0 in the bottom piece and work that out, and we're done. At this point, it's important to note what we're actually finding. If we plug in an x, the output would be f of x, which is y. So what we're actually generating are ordered pairs. So far, we have the ordered pair negative 2, 4. and the ordered pair 0, -1. If you generate enough ordered pairs, you can generate a graph of this piecewise function. So now that we've covered how to evaluate a piecewise function, how to determine which piece to plug x into, let's cover a technique for graphing a piecewise function. What you want to do is construct a table of values where you're going to need to pick at least 2 values of x for each piece. Also, the number in the inequality that matches, here it's a 0, that is called the transition point. And even though it doesn't technically go in each piece, you have to plug it into each piece to determine the actual points on the graph. So since 0 is our transition point, we are going to have to use 0 twice and plug it into each piece of the piecewise function to determine those 2 points. And I'm going to put a line here to delineate that all of the x's I choose above the line are going to go in the top piece of the function, and then all of the x's below this line will plug into the bottom piece of the function. Okay, so plugging 0 into the top piece first, 0 squared is 0, so I will have the ordered pair 0, 0. Notice according to the inequality, 0 does not technically fit there because 0 is not less than 0. And I'm going to designate this as open. On the graph, we will represent that point with an open circle because it's not actually a point on the graph. In the bottom piece, 2 times 0 minus 1 is -1, and that point will be solid. And the reason it's solid on the graph is because 0 does belong there. 0 is greater than or equal to 0, so that is an actual point on the graph. Now, since the top piece is quadratic, I'm going to pick at least 2 more x's just so that I can get a feel for where the parabola goes. So I'm going to choose -1 and -2. And then I need to evaluate the top piece of the function. Again, you understand I'm picking -1 and -2 because those numbers are less than 0, so they belong in the top piece. So plugging in, -1 squared is 1, giving me the ordered pair -1, 1. And -2 squared is 4. Giving me the ordered pair -2, 4, and that should be enough points to determine the graph for the top piece of the function. If I need more definition, I can choose more x values. And for the bottom piece, we need to pick an x that is greater than or equal to 0. Greater than 0, we could go with 1, 2, 3, pretty much any x value. I'm going to stay close to home and choose 1. And since 1 is greater than or equal to 0, we're going to plug that into the bottom piece and work it out. That's going to be 2 minus 1, which is 1. And if you noticed, the bottom piece is actually slope-intercept form. Remember, f of x is y. We've got y equals mx plus b. And we know the minimum number of points to make a line is 2. So that should be adequate for the bottom piece. Now to the coordinate system. Let's plot our points. First, I've got -2, 4. Next, -1, 1. And 0, 0, the origin's going to be an open circle. Remember that for values less than 0, which would be anything left of the origin, they're going to be quadratic. So we should see a parabola, something like that. So we feel good about that because the points that we plotted actually fit on a parabola. Next, we've got 0, -1, which is a solid dot, and 1, 1. And we're going to connect those dots with a line because every x greater than or equal to 0, which would be all of the x values to the right of the origin, including the origin, fall on this piece of the function. And we again know that that is linear because the bottom piece is slope-intercept form. And this covers how to graph a piecewise function. And just for fun, I thought we should look at a piecewise function that's a little more exciting. This one has 3 pieces. Remember, at the back we have the test zone where you need to take each x and test it to see where to put it. And since we have 3 pieces, notice that we do have 2 transition points. So -1 is where we transition from the top to the middle, and then +1 is where we transition from the middle to the bottom. So to start our graph, remember we need to make a table of values. Since the top piece is quadratic, we probably should use at least 3 values of x, and one of them needs to be the transition point. So I'm going to say -1, and then remember for x's less than or equal to -1, we use the top piece. So I need 2 more x's less than or equal to -1. Let's stay close to home, -2 and -3. Then we need to use -1 again. Remember the transition points have to be used twice. The middle piece is a constant function, so no matter what x is between -1 and 1, the y value will be 4. So we know if x is -1, we're going to get 4. Since this is strictly less than, this point is going to be an open circle because -1 doesn't technically belong there, but it is going to tell us where the graph gets close to as it approaches -1 from the right. We also need to use the other transition point, +1. It will produce a y value of 4. Remember that whatever x is, for the middle piece, y is going to be 4. And this also will be an open circle because 1 doesn't technically belong in the middle piece. Again, we need to use the transition points twice. So we're going to use 1 for the bottom piece. Now here you can see that 1 is greater than or equal to 1, so this will be an actual point on the circle. If I plug it in to the bottom piece, we're going to get 3 minus 2, which is 1. This will be a solid dot, remember, because it actually belongs there. And since this bottom piece is linear, remember we're going to have y equals mx plus b. It is slope-intercept form. I only need 1 more value of x for the bottom piece. And again, I like to stay close to home, so I'm just going to go with 2. Plugging that into the bottom piece, 3 times 2 minus 2. 6 minus 2 is 4. And the last thing I need to do to complete this table is plug my x's into the top piece. Okay, here we go. Plug in -3 in for x into the top piece of the function. We're going to get -2 quantity squared, which is 4. Next, -2 plus 1 squared. That's -1 quantity squared, which is 1. And last but not least, -1 plus 1 quantity squared, which is 0 squared, which is 0. And that also will be a solid dot. Remember, because -1 is less than or equal to -1 is a true statement. Now I should have enough information to sketch an accurate graph of this piecewise function. Going to the xy coordinate system, plotting our points, we're going to have -3, 4. -2, 1, and -1, 0. Remember, that is a solid dot. Also remember that this top piece is quadratic, so we will expect a parabola. The middle piece was a constant function. At -1, we're going to have an open circle at 4. And at +1, we're also going to have an open circle at 4. We're going to connect those dots straight across. And just for reference, remember back at the very beginning of the lesson, we know that a constant function has a y equal to some value. Here it's equal to 4. We would expect a horizontal line at 4. And that is what we get for the middle piece of the function. Last, 1, 1 is a solid dot, 2, 4. And if I connect those points, making a line, I get the last piece of the piecewise function. And that should be it for that particular function. Now, the last thing I'd like to cover in this lesson is how you can use Desmos to check your piecewise functions. So for our piecewise function, we had f of x equals, on the top, x plus 1 quantity squared. So what we want to do in Desmos is in the first equation line, we want to input the top piece of the function, like so. But since the top piece was restricted to x less than or equal to -1, we're going to have to input that restriction in Desmos. And here's how you do that. We're going to open up the keyboard. You're going to click the ABC button, and we're going to click the braces button. Remember that braces are used to indicate a set. And for the top piece, we want to reduce the set of x's allowed to be x less than or equal to -1. So we're going to type in x is less than or equal to -1. And then if I hit enter, we can see that we have that piece of the piecewise function all the way up to -1, 0. And then you're going to rinse and repeat for the middle and bottom pieces. Next, we're going to say f of x equals 4. Again, that's going to give us what we thought, the constant function, which is a horizontal line, and we need to restrict the domain again. So back to the ABC button, grab another set of braces, and if you remember the restriction here, you're going to input that just the way it looks. -1 less than x less than 1. And enter. And if I blow that up again, you're going to see here that we have our constant piece. Not only that, if you click on that section and hold it and drag over, you're going to see that it does indeed show that those endpoints should be open circles, just like we had on our graph. And to check the last piece of the function, we're going to input f of x equals 3x minus 2. And then don't forget, we need to restrict the domain. Grabbing another set of braces, this time x must be greater than or equal to 1. And there is the last piece of the graph. So what I'd like to do is let's blow that up a bit. Click and drag. We can see we've got our solid dot. Open circles on either end there. And solid dot up. Notice this graph matches this graph exactly. And that's how you can use Desmos to check your piecewise function graphs. And that's going to do it for this lesson. So if you have any questions or comments about anything that I covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.